moved Algebra to section 5.1, use of properties of exponents. We're going to revisit some of the things that we had picked up in Algebra 1 regarding exponents. There's a long list of properties that we're going to take a look at. I would recommend that you read through the textbook. Again, hopefully you're doing that the night before, kind of get some ideas about what we're doing, but also to develop some questions you might have regarding what you're reading. All right, when we manipulate exponential numbers, it's beneficial for us to be able to use these properties to simplify our number. And we can do that through product, where we're multiplying exponential numbers together. We can do it through the quotient, where we're dividing exponential numbers. We do have some special circumstances with negative exponents or zeros, and we're going to take a look at all of those. All right, the thing to remember with the properties of exponents is that it's important that we recognize that we're working with real numbers as our bases. And the bases are those numbers, or could be variables, that are being raised to a power. And so in this case, these guys, also known as exponents, are going to be my powers. And those powers are going to be integers, so they can be positive or negative. We will eventually take a look at what happens when they're fractional. So it's important when we're working with product or quotient that we have the same base, as in this first example here, a to the m power times a to the n. So two different base exponential values multiplying together means I can rewrite them as one base number with the sum of their powers, m plus n. And here we have some examples over here on the right side. 5 to the third times 5 to the negative 1 means you can simply write that as 5 to the 3 plus negative 1, or 3 minus 1, or 5 squared, which is just 25. So that's our product of powers, where we have two different bases. Unlike our power of powers, we're end up with just one base, and then I have two exponents multiplying together. So when I see this one base parenthesis with another exponent, I'm thinking about this powers, where I'm going to be taking the product of my exponents versus the sum of my exponents. The next one, power of a product. Now we have multiple bases being raised to the same power. And in this case, that means we raise to the power of m everything inside of this parenthesis. So a gets raised to the power of m, b gets raised to the power of m. We end up with that. Negative and zeros, these are our two unique circumstances here. We'll talk about where the zero comes from in just a second. But negative exponents. We want to write all of our exponential solutions as positive. And so we need to do this kicking out of upstairs, downstairs is what I refer to it as. Our negative exponents will reside either as a numerator or a denominator. And in this case, with the example of a to the negative m power, it's like I'm having a 1 down there as a denominator. This helps me establish what's, quote, upstairs, what's downstairs. And if I want to rewrite a negative exponent as positive, I simply move it to the other location. So move it from the numerator to the denominator, or from the denominator to the numerator. And that's what's happened here. So a to the negative m is the same thing as 1 over a to the m. A common mistake on that is, like we'll use this one here as an example. Common mistake on this is that people say that 7 to the negative 2 power is negative 49. And it's not. It's 1 over 49. So just be careful with those negative exponents. Always move them somewhere else, either into the numerator or the denominator, to make a positive. The zero exponent. How does anything to the 0 power equal a 1? Again, we'll use another example. We're going to use our quotient of powers to demonstrate this. Let's say we had, as a quotient of power, we had a 5 to the third divided by 5 to the third. Well, we know that 5 to the third over 5 to the third, anytime I divide the same thing, I get a 1. But we also can find out with our next power here, quotient of powers, that when I'm dividing like bases with exponents, I can rewrite that as 5 and then subtract the exponents. Well, that becomes 5 to the 0. So that means 5 to the 0, and quotient of powers, again, two bases, two different exponents. Now we're subtracting. So product is adding powers. Quotient is the subtraction of those powers. And then finally, the power of quotient. Fraction raised to a common power. We distribute that power raised to the power of m, each of those values of that fraction there, a to the m over b to the m. And these, just be careful with these notes here. I can't ever have a base that's, base can't be a 0. Otherwise, I'd be dividing by something at 0, it would be undefined. So those are our properties we're going to work with now for these. And this section is just a lot of, we're going to do some skill work here. See if we can just manipulate these things. All right. Let's just go ahead and take care of these first 4. Again, as I'm working through them, if you want to practice on your own without me running through the example first, make sure you just pause the video. All right, on this first one here, we recognize that I've got different bases. And I've got them inside of a grouping symbol, parentheses, and then this power of 3 on the outside. So I have a situation where I'm going to raise the power of 3, everything on the inside of this parentheses. This is my power of powers. If I did that, I'd have a negative 3 squared, and that's getting raised to the power of 3. And then I have a 5 being raised to the power of 3. Now, we have to be careful with these negatives that are showing up in front of our bases. Negative 3 squared does not equal the same thing as the quantity negative 3 squared. In the first one, the base is the 3, not the negative. So this is negative 9. In the second example, the base is a negative 3. And when I square that, I get a positive 9. So be careful with these negative numbers that appear to be hanging out in front of our base. If those negatives are not included in some sort of a grouping symbol and then a power, then that negative is just going to be part of my solution there. All right, so we go back to this one. We get negative 3, and then this is the power of powers. 2 times 3 is 6. And 5 to the third. And this becomes negative 729 and 125. This becomes negative 729 times 125. Negative 91,125. All right, on B, we have that negative exponent there. Now, there's 2 approaches that we could work with these negative exponents. We have a fraction or a quotient like this with a negative power applying for the entire quotient. There are 2 things you could do. Thing number 1 is you could just write the reciprocal of that fraction. So I could write 3 to the negative 2, 1 to the 4th, and now this would be a positive power. Or the second option would be to raise to the power of negative 2. So we leave this written as it currently is. And we raise to the power of negative 2 all of the powers inside. All right, both ways. So even here with the step 1, method 1, I raise to the power of 2, the 3 to the negative 2, and I get 3 to the negative 4th. And 4 times 2 is 1 to the 8th. And then the negative exponent needs to move down here to create a positive exponent on the bottom. Now, when you move a negative exponent down, you're not leaving a 0 up there. It's actually a 1 that's still up there. So this is a 1 over 3 to the 4th times 1 to the 8th, which is 1 over 81. On the second method, I would have had 1 to the negative We have powers, 6 to the 6th. And if we wanted to take that out, 46,656. On D, we've got a quotient, which means I can subtract the exponents. We get 4 squared or 16. Okay, scientific notation, how this plays out with the exponential properties is we have in scientific notation, a part of our scientific notation number involves an exponent of a base 10. And this C value, the integer that's hanging out in front for our scientific notation, must obey this. It must be a number that's less than 10 but greater than or equal to 1. That power in is still just an integer. So there are actually a couple different approaches we could do to scientific notation when we're writing our solutions. Since we're focusing on the exponential part of it, working with the power properties of exponents, that's what we will look at for these examples here. All right, so again, being careful with the fact that I want my C value, I want that thing to be a number between 1 and 10. Here are some general rules with scientific notation. If C is less than 1, then N is negative. And if C is greater than or equal to 1, then N is going to be a positive exponent. All right, so we're going to work at the approach from some scientific notation using our exponential properties. How would we do that? 400 we would change and write as a scientific notation number, and 250,000 we will change and write as a scientific notation number. So first, the 400. How do we take a number and convert it into scientific notation? Well, we first of all consider where the decimal is. And in 400, the decimal's at the end. And that decimal, to make a number between 1 and 10, would have to move 2 places to the left. And then that number would become 4.0. Well, when I move my decimals to the left or the right from an original integer number, or a whole number in this case, I end up having to account for that movement with my exponent, this power of 10 to some power thing. And how you account for the movement is determined on whether or not that number that it started with, in this case 400, is obeying one of the 2 rules we just stated above. So since 400 is a number that when we change it to a number between 1 and 10, it started out as a number that's bigger than 1. We're going to end up with positive exponents here. Or another way of thinking of it is, if I'm sitting at 4.0 and I'm to try and create from that a 400, thinking about movement of my decimal, I would have to move my decimal 2 to the right, which means 4 times 10 to the second is the same thing as 400. Same line of thinking with 250,000. Your decimal is at the end of the number, and it would have to move 5 places to create 2.5. And because 250,000 started as a number greater than 1, my exponential value will be positive. And again, thinking about where would I take the 2.5, move the decimal 5 places to the right, and I get 250,000. So if we do that, we have 4 times 10 to the second, and we're going to multiply that by 2.5 times 10 to the fifth. And now here's where our properties of exponents work together. First, we consider the C values, and we work with them independently of the exponential values. So thinking about the exponential values, since that's what we're kind of concentrating on, I have a 10 to the second times a 10 to the fifth. And that means I have a product of powers, which means I add powers together, and I get a 10 to the seventh. Now what we do with the 4 and the 2.5 is we multiply them together. This equals 10. c being between 1 and less than 10. So we need to kick that decimal back to the left 1. So the 10 needs to become a 1.0. And thinking about moving that decimal back to the left 1 meant that I would have to add a power on my exponent. And so I get 1 times 10 to the 8th. So what about this one? We have already set up an exponential form with scientific notation, so it's the same thing. I still consider looking at the c values, and I divide them, and then I still consider the exponential values, and they also are being divided. So we're just separating it here. And then we do a 2.94 divided by 1.03, and we get a 2.83. 2.85, sorry. So the red gives us 2.85. There's our c value, and it fits. It's in between 1 and 10, so that's good. And then our exponential, we have quotient powers, so I have 10 to the 5 minus 5, 10 to the 0, so I end up with 2.85 times 10 to the 0. Well, this whole thing just becomes 1. My final answer can just be written as 2.85. All right, so there's our scientific expression and scientific notation kind of working within the world of our properties. All right, we're going to try these out. So the next couple sets of problems are just some review, and we're going to add more and more things to this. Recognizing for A, 3 bases that are W, which means I can add their powers together. Now, some of you might have taken an issue with the fact that that's a W to the negative 8th, and maybe you thought, hey, I should move that down to make it a positive. Well, you're going to get the same answer regardless, so let's see how this works. 5 minus 8 is negative 3. Negative 3 plus 6 means this is W cubed. Now, what if you had moved that W to the negative 8 as a positive exponent by moving it down? Then you can get W to the 5 plus 6 over W to the 8, or W to the 11 over W to the 8, which is W to the 11 minus 8, which is equal to W to the 3rd. So you might be one of those folks that just likes to make all your exponents, negative exponents, positives first before you start working out the problem. That's okay too. All right, here we go. B. I raised power here. C to the negative 2 power. D to the negative 4th to the negative 2 power. So C to the negative 2, D to the 8. And then I kick the negative exponent downstairs. 1 over C squared D to the 8. Here, I recognize I have like bases in the numerator and the denominator, so I could, if I wanted to, just start with subtracting those exponents. This becomes a to the negative 8 b squared, and then I got to kick that guy downstairs, which means the b squared stays as the numerator, and the a to the negative 8 will move down to become an a to the positive 8. And then here we had a little more stuff going on inside of the grouping symbols there, so being careful here. Raising to the power, I got a power of powers happening. I've got some quotient of powers going on. But I got to remember when I have a power on that outside that I raise to the power everything. Even if something doesn't have a power, such as this 2. It's 2 to the 1st, but I raised everything to the power of 3. So all of those are going to get raised. It now looks like a squared to the power of 3, b to the negative 1st to this just becomes a to the 6th, b to the negative 3rd, so I'm going to have some moving I have to do maybe. 2 to the 3rd is 8, a to the 9th, b to the 6th. All right, so at this point, maybe you decide you want to do your quotient. And you say a to the 6th minus 9, b to the negative 3 minus the 6, and then that just leaves me with my 8 in the denominator. But this becomes a to the negative 3rd, b to the negative 9th, which means both of these guys have to get kicked out of the numerator and put down into the denominator. And end up with this, which is the answer D. All right, we're looking at a volume problem here. So the volume of a sphere, ball, planet, is equal to 4/3 pi r cubed. And we have the radius of Jupiter is about 11 times greater than the radius of the Earth. How many times greater is the volume of Jupiter than that of Earth? All right, so we can say something like this. Volume of Jupiter is equal to 4/3 pi, the radius of Jupiter, cubed. And the volume of Earth would equal 4/3 pi, the radius of Earth, cubed. But we know that the radius of Jupiter is 11 times that of Earth. So we can say this. The radius of Jupiter is 11 times the radius of Earth. All right. So we don't actually have a value for the radius of Earth. We can go find that if we wanted to. But the fact is, it is 11 times bigger radius-wise. So what does that do then to my my volume? Does it make my volume 11 times as big as well? Like I said, you don't need to know the number for the radius of Earth. So if we just simply reference radius of Earth here, we see first of all that in these volume problems, this is a constant for both Earth and Jupiter. That's not going to change. So our volume will change relative to what our radius is doing. And our radius for Jupiter is 11 times that of Earth. So let's just arbitrarily assume our radius of Earth was 1. Well, our radius of Jupiter then would be 11 times 1, or 11 radius of Earths. And therefore, I got a situation where I can do this. I have radius of Jupiter, 11 radius Earth, and radius of Jupiter cubed would mean I'm just raising to the power 11. And that means I have 1,331 times larger. So that's how many times greater our volume would be, Jupiter to Earth, simply looking at the radius and cubing that. There we go. I hope that was helpful. We'll see you next time.